Right. So what we saw yesterday was some properties of the eta invariant and how to use it to define the phase of the partition function of a fermion. I haven't been so far very explicit whether I'm talking about local or global anomalies, and that's because eta encodes both, but I want to make that distinction now. So let me start with the expression that I reviewed yesterday, the APS index theorem. Eta is in some manifold n, which is d plus 1 dimensional, so the thing that gives the phase, is the index of the Dirac operator in some manifold Z, minus the integral in Z, so this is d plus 2 dimensional, of the air of genus in Z, times the Chern character of whichever bundle the fermion is coupling to. And in writing this expression, I'm assuming that the boundary of Z is n. I think I called this S yesterday, so let me start with that maybe. Okay. So this is going to be our starting point for distinguishing between local and global anomalies. As I explained yesterday, local anomalies.
Excuse me. Yeah. We have index of Dirac operator defined on the top S. So that would depend on the boundary condition. So whether there's some special choice boundary condition, specified here.
Yeah, sorry. Yes. This is with APS boundary conditions.
The way to choose this boundary condition.
Yeah, sorry. This is implicit in my whole discussion. Yeah. These are not the most physical boundary conditions. The more physical ones are ones that are more physical, let's say, are ones that Yonekura and Witten studied. There's a different set of boundary conditions. In the paper, they study the relation between the two sets of boundary conditions and how you can reproduce the argument that I gave for the phase from the point of their boundary conditions and how that relates to the standard definition by Diane-Fried. The discussion is a bit technical, it will take me too long, but the details are explained there. So this is Yonekura and Witten. Of course, Diane-Fried also say this, but this is the physical sort of picture.
But there's also similar for the second term. Also, we need to specify near the boundary how the curvature, or maybe is a constant curvature independent near the boundary the curvature and independent of a normal direction or some special boundary condition.
There's some special conditions in this theorem. Yeah, basically, the important bit is what happens to the Dirac fermions, to the fermions in the boundary. Here, what you want is your bundles to go to the constant bundles that you have.
Can you just say what is this APS one?
Yeah, it's a non-local boundary condition where you say something about the spectrum of the Dirac operator as it approaches the boundary. You want it to be chiral in some way. Yeah. This is a very good discussion. Yeah. All right. So, as I discussed yesterday, local anomalies are encoded in, let me call this I. So I'm going to call the local index density I. So whenever this combination is not vanishing, we say that we have a local anomaly. The motivation can be understood from what I explained yesterday between the relation of the eta invariant and the Chern-Simons invariant, if you like. Once you have that relation, you can reproduce standard anomaly descent formulas. Or more simply, remember that this encoded for us what happened to the phase under small deformations. So these are going to be the local bits. So the first thing you have to do, if you are seeing if if a theory is anomaly free or not, is to see if the anomaly polynomial vanishes or not. So first you want to check whether if the index density does not vanish, then you have a local anomaly, and that's the end of the story. You cannot really fix this if you want to gauge. So let's see what happens when the index density is 0. So for now, assume that the index density is 0. Then the following nice thing happens. The thing that gave us the phase for the eta invariant, so the phase for the partition function was the eta invariant, and so this is an n. And let's assume, as before, that n is the boundary of some s. I'll drop this assumption in a second, but let's assume this for the moment. Then I can use the APS index theorem to write this as e to the 2 pi I, index of the Dirac operator on S, minus the integral on S of the root genus and the Chern character. All right. So this thing here is an integer. The index is the dimension of some vector space minus the dimension of some other vector space. There's an assumption here that the Dirac operator is well behaved enough that this expression makes sense. So I can count dimensions in this way. And by assumption, this is 0. So I have e to the 2 pi I times an integer, and this is equal to 1. So that tells me that whenever my n is the boundary of some s, and I have no local anomalies, I can define, I can compute this thing, and it's just 1. Now, this does not mean the theory is anomaly free, because this assumption is quite strong. Not every manifold is the boundary of some other manifold. So I think this is something that Max discussed already. Max. Okay. So this implies that e to the 2 pi eta is a Bordism invariant. In particular, it's a homomorphism from the D+1 spin Bordism group of some classifying space to U1. I know that Max did something about Bordism, but is that expression sort of obvious to everybody? Is that something Max covered? If not, I can unpack it. Just don't want to repeat things.
Well, I think he discussed homodism and also. Yeah.
Okay, so this is familiar to everybody?
Yes.
Yeah, okay, good. All right, so.
I guess the notation with the classifying space might have not been mentioned like that. But,
yeah, that's true. Classifying space, BG was not defined.
BG was not defined, okay. Very good. So let me do that. Maybe let me explain BG and then explain this notation. And then maybe we'll compute an example of this.
Here I have a general question. If in the presence of a perturbed anomaly that's I not equal to 0, can you define global anomaly? From here, this seems to have some difficulties.
I wouldn't know how to do that because, for example, in the picture of the global anomaly as some holonomy, if the bundle is not flat, you know, and you're trying to compute a holonomy like this, and then you wiggle a little bit, you're going to get something different. So I don't know how to give meaning to a global anomaly in the presence of a local one.
So therefore, in the presence of a perturbed anomaly, the global anomaly may be not defined or not present or something.
That would be my take. Yeah, I wouldn't know how to define it here. Yeah. Any other questions? Okay. So yeah, let me define what this is. So for that, I want to introduce the notion of a classifying space of a group. By the way, I should say, so far here I'm talking about zero-form symmetries. There's generalizations of these to higher form symmetries, higher groups, things like that. But let me do the simplest case. So say that you have some manifold. Here I'm thinking about n. And I put a principal bundle on it. I call it PG on n. So as usual, you should think of this as n with a copy of G over every point and the glue in some non-trivial way. The idea of classifying a space is an idea for classifying these sort of principal bundles through a universal construction. So you sort of invert the arrow in some sense. So for each group that you can use for constructing a principal bundle, this is an associated classifying space with the property that principal bundles over n are classified from maps from n to Bg. And more precisely, there's a universal bundle over Bg, and the pullback of this universal bundle gives you a principal bundle. Of course, constructing these classifying spaces and analyzing their properties can be difficult, but I'll give you examples in a second. So maybe let me do a couple of examples. So G and Bg. If you take set 2 as your group, the simply discrete space, one model that you can construct for Bg, that is, if you want to classify all possible Bg bundles, you can take Rp infinity. So take Rpn and send the n to infinity. There's a better definition of this. If you have U1, you can construct Cp infinity. This is also sometimes known as, sorry, I should have this, say this. This is K set to 1 for people who know. And this is K U11, U12, U1. And finally, the one I will explain later. For SG2, your classifying space is H P infinity. Yeah.
So this G is now related to the background B that you chose with yesterday.
Yeah.
But yesterday the background B could be anything. Could be either a normal gauge, background gauge field, or a background metric, or anything.
Right.
If it was a background metric or something else, what would the equivalent G be?
Yeah, right. So that's sort of a split in here. Right. So when talking about the spin bundles, I'm thinking, well, first of all, this is only going to be relevant in the case, as I will explain in a second, as I have explained, that you're talking about bordism. So small deformations are not going to matter, small deformations of the metric are not going to matter. But you might care about the spin structure, and that's included in here.
Yeah, would it take too much time to consider some example of a map, say, of n into Rp infinity or some particular map, and explaining how it's pulled back this Z2 bundle over n? Because I don't understand how pullback would.
Yeah.
There's no Z2 anywhere in this construction, so why would you, when you take a pullback, you would get a Z2 bundle and not anything else?
Yeah. I can do that next lecture probably. On the fly, I'll probably make mistakes, and I don't want to do that. But the basic idea is here, if you look at this Rp infinity, you have pi 1s of torsion. So let me, maybe the thing I should say. Bg can be constructed in general as a quotient to some space, which is called Eg, which is relatively simple, mod G. So the information about G is in the fact that you have this quotient here. As you construct this universal, so this space is basically a point. It's contractible to a point in homotopy. So it doesn't have a lot of information. But as you quotient by G, you're going to pick up the action of G on the transition function. And then by pullback, that's the thing that gives you the transition functions on your manifold. If you want, I'm more than happy to do it in the next lecture. I haven't prepared notes, so I'm not sure I can give more details at this.
Here, this omega is a Baudism class if BG is trivial. But if BG is not trivial, what is omega BG?
Oh, yeah. Right. So I'm going to answer your question. So let me just state, and I'm happy to give the proof next lecture, that principal bundles can be understood as pullbacks of such maps. So I can construct both things in the same way. Now imagine that in the definition that Max gave for Bordism, you have some manifolds that are connected. You can decorate these manifolds, all of them, with maps to BG. That's the same data. Exactly. That's the same thing as saying that you put principal bundles in all of them.
So this back extend to the bulk.
Excellent. So you do the same construction, saying that I keep the extension to the bulk consistent. I keep the maps to BG, the glue properly as I extend to the bulk. Yeah. Yeah.
Thank you.
So that's what it means. Okay.
Another to say that this cobordism of the manifold equipped with principal bundle.
Yeah, exactly.
Principal bundle can also extend to the bulk.
That's correct. Exactly. When you do this extension, everything extends to the bulk. This BG, from that point of view, might seem a little bit why I do this, and you might think of this just as notation. But there's a deeper meaning of this that will come useful in a second. So you can think of this omega d plus 1 spin as a homology group of this space. And then this space acquires a life by itself. You're computing a sort of homology group of this. Okay. So yeah. Oh no. Okay. So there's a second step now. For checking the absence of anomalies is the absence of global anomalies. You want this object to be defined unambiguously. You want the phase of the partition function to be defined unambiguously. And that means that this object should evaluate to 1, not only on boundaries, but on any representative of your Bordism class. So you want to check that e to the 2 pi I theta of the Dirac operator on some manifold n is equal to 1 for all n, but you can, because this is a Bordism problem, so you can restrict to a single convenient n inside each okay. So the implication of this formal formula, that this is a homomorphism from Bordism to U1, means that you just pick one representative of each class and you compute there. It's typically very difficult to compute data invariants, but with enough cleverness, very often you can compute for some specific simple representative.
There's another question. Well, this eta inverse generates the full this cobordism, this home of omega u, or only generate a subgroup of that.
Yeah, that's correct. So you're supposed to compute the eta invariant for the representation where your matter lives. So it's perfectly possible that you get non-trivial Bordism groups, but when you evaluate the eta invariant on those, you get 1 for your representation. Yeah. Say perhaps less, in less detail. If you have a theory, say, NSU2 anomaly, it's perfectly possible that the particles with half integral spin have some issue, but the integral spin ones don't.
A small question. I didn't quite follow the logic here. If this manifold N is not a boundary of some paradigm manifold S, how to proceed with the first step that you wrote?
This one is a local statement of the anomaly polynomial. It doesn't really require me to pick an S. I'm saying that this thing as a differential form is 0. Yeah?
You need an S, no?
Yeah?
But don't you need an S for it?
Well, you can do a formal thing. So this thing is a differential form that depends on the local curvature. So remember that this is something that depends on R. It was the determinant of 1 plus R. And this thing is something that depends on F. So expand in terms of R and F, and you want to see that this vanishes as a function of R.
So you probably mean for particular matter content.
Yeah, this is always for particular matter content. Yeah.
Do you need the whole thing to vanish? Sorry, or do you only need the term of the d plus 2?
Oh, yes, yeah, of course. That's what I mean by this notation.
Okay.
But I wasn't super careful when I wrote that. So here I pick the piece of the bar that integrates to non-zero. And I'm defining this to be I d plus 2. Yeah.
Sorry, can you just remind us the definition of the Bordism? Because like in Max class, it was kind of, there is this addition operation which we glue the spaces. But when we have this BG inside,
it's the same operation, but you keep track of the maps. So every time you glue, you impose that the boundaries that you're gluing, the map to BG on those boundaries agrees.
Oh, I see. That was what you were at.
Yeah. So it's basically exactly the same definition decorated with maps to some space.
I see.
And the space is this BG. By the way, I emphasize the definition of Bordism as Bordism of something. This object does not have to be B of a space, any space will do. But we're interested in the case of BGs, which are a specific kind of spaces. Yes.
Sorry, so in each board, is it true that in each Bordism class you can have n being the boundary of something, or is that not true?
No, it's the opposite, precisely. If something is a non-trivial Bordism, if some manifold n is representative of a non-trivial Bordism class, it cannot be a boundary.
So why did you assume that n is the boundary of something?
If you assume that n is a boundary, then I can prove that the eta invariant on that n is 1, so the exponential of eta invariant is 1. That's compatible with this definition. The homomorphism, the only homomorphism from 0 to U1 is the one that sends to identity. But in general, you're going to have things which are not boundaries. Then I cannot apply this proof.
Well, you can, but it just tells you that it's a Bordism invariant. Right? It will tell you that.
Well, yes. If I compare the two boundaries, exactly. Exactly. Yeah.
Yeah, I could repeat my previous question. Is in physical, this eta invariance describe anomaly for non-interacting fermion. It's not fermion field theory. And then this Bordism classify all possible anomalies, we believe. So there's a possibility whether there's certain anomaly cannot be realized by non-interacting system. You have to have an interacting system. So that's my question, is that whether this eta invariance can realize or generate all this Bordism classification by choosing different representation as you emphasized.
Yeah. That's a good question. I know only partial results in this direction. Okay. Yeah, so there are some partial results that relate this to K-theory.
Okay.
And in those cases, you can... So the eta invariant is basically the K-theory realized locally. Yeah. And in those cases, then you can prove it. But these results, as far as I know them, they are partial. I don't know a theorem that tells me, it's a bit frustrating because I don't know a theorem that tells me that I can always capture these things, and I don't know a counterexample, so I don't know the status of this.
I see.
Yeah, it's a good question. Yeah.
So you're done with it in the step 2? Or is there a step 3?
No. Step 3 is success.
So strictly speaking, as he says, we check the necessary conditions, but not necessarily sufficient conditions.
Oh yeah, let me say something about that. If these two conditions hold, it means that you can define the partition function unambiguously using the prescription by die and Fried. In that case, we just say that there's no anomaly by definition. The anomaly was an ambiguity on the face, and we are given a prescription that uniquely determines the face.
Let's see, even if we start with a completely general matter content, although you said they fix the matter content.
Yeah, that we fix from the beginning, yeah. We have a theory that we like, and we want to see if it's anomaly free or not. There's a different question whether you can realize all these homomorphisms with some matter content, was the previous question, and for that I don't know the answer. I don't know a counterexample also. Every example I know you can capture everything, if they're clever enough.
So it is necessary and sufficient. Why is it only necessary? I don't understand.
Well, if you have some specific theory, I think there are two ongoing questions which are a bit different. One is, do you have an anomaly? And for some specific theory. In that theory, you have some representations, and then you're supposed to construct data invariant for those representations and check. If that's one for every Bordism class, you are done. So that's the necessary and sufficient condition for anomaly to be, for a theory to be anomaly free. There's also the issue, if you have a class of Bordism class, so you have some Bordism representatives, can you detect these Bordism representatives with the data invariant of some matter content? Yeah, that's different. Sorry. Is there always a theory that realizes this anomaly?
So we have one more question.
Yeah.
I still got kind of confused. I thought the first equation you wrote assumes n is a boundary of some hierarchy.
Yeah.
Don't assume that why checking this I sub p plus 0 implies. I mean, I still.
That one, the second. Sorry, I skipped some steps there because I thought Max had covered them, but because there have been a couple of questions, maybe I can do the argument here. So here's the idea. Imagine that you have some n and some other n prime. And let's assume that the class of n is the class of n prime in Bordism. Say d plus 1 spin, or whatever it is, really, in whichever Bordism group you are in. That means that I can construct some manifold here that connects them. So, as Slava was saying before, if you now construct this manifold, let me call it Z. No, S. Now the boundary of S is n prime minus n. I have that n prime minus n is a boundary, so I can apply that proof. So that implies that e to the 2 pi I eta invariant of the Dirac operator in n prime minus n is equal to 1 in the absence of local anomalies. But by the properties of the eta invariant, this means that the eta invariant in n is equal to the eta invariant, slashes everywhere, n prime. Yeah. So this tells me that any two things that are connected by Bordism share the same eta invariant in the absence of local anomalies. And the fact that the homomorphism is clear, and the fact that goes to U1 is clear. Yeah. Very good. Okay. Maybe let me say something that there was a couple of questions about this yesterday, and they are good questions. So I want to now address them head on. In the classical picture of anomalies, the thing you want to do is to define the path integral starting from a point, and you want to see if the phase is giving you trouble as you make little loops in your configuration space. And the natural object there is mapping tori. So you want to construct something that you start with an M and a B, and you move in configuration space, and you end up with an M and maybe some gauge transform of B. As I explain later, the prescription of the data invariant helps you here still, because it can give you the difference in the phases of these two as you parallel transport. But what I'm posing here is more general. I'm not just saying that there's no ambiguity as you do these little loops. I'm saying that you can fix the phase unambiguously. So that's stronger. Diaphragm is indeed stronger. So, sorry. I just changed the order of the title, but yeah, so it matches the picture. So you have mapping tori here, and the picture of diaphragm is more that data invariant on any manifold that you obtain, not just the gluing of these two ends, is equal to 0 mod 1. So, in fact, these two conditions are different, and they give you different answers. So, if you want to go examples, there are many by now. Some of the earlier ones that are nice are 1508. Also, Juven, I don't know if Juven's around, Juven has a series of papers that are very nice, where he also studies this and he finds constraints that are not apparent in the mapping torus. But to me, at least, a question that should be asked is whether we really need to impose this condition, or it's enough to impose the mapping torus condition. So I don't have an answer in field theory, but in string theory, I think it's natural to think of this condition. And although I don't know a theorem or anything like that, my intuition here is the following. Imagine you have a mapping torus and in field theory, but this mapping torus might not generate all the Bordism classes. Sorry, as to say. Not all Bordism classes can be generated by mapping tori in general. There's the reason for these examples. But the thing that you can always do is take your favorite mapping torus, even the trivial one, and do a connected sum with some generator of Bordism. By the way, nothing I'm going to say in the next couple of minutes is going to be a theorem or anything like that. It's my intuition for why this is the right thing to look at. Okay. So you think of the connected sum of these two spaces. That means you glue them along some little region. And up to the formation, you're going to end up with a space that looks like this. Some generalized mapping torus, but it's going to be a generic Bordism between these two endpoints. Now, in field theory, there was no reason to change our manifold M as we went along, only we changed the bundle. But in string theory, if you think of what's happening here, as you take slices, what's happening is that M is undergoing topology change. It's splitting into pieces, getting handles, and so on. So if you accept that your configuration space includes topology change, you end up with pictures that look like this. And when you glue, it's reasonable to conjecture, although as far as I know there's no proof, that this kind of spaces can reproduce all the Bordism classes. This generalized mapping tori can realize all the Bordism classes. So in quantum gravity and string theory, this seems to be the right condition, certainly. We know that topology can change as you go along. And it seems reasonable then to impose this condition, which is stronger than that one. Okay, so let's do an example. Yeah. So I'm going to take the four-dimensional theory of a Weyl fermion. Here's a famous example. In the fundamental of SG2. So this is, of course, the famous paper by Witten on the SG2 anomaly. And I should say there's a much more recent generalization of this story, which is very interesting. I will not cover it because it's a little bit more advanced, but it's definitely something you can hopefully read after this lecture. By Juven, Xiaogang, and Witten, where they study also the SG2 theory, using this die-free sort of point of view and define new anomalies beyond the one I'm going to explain. Okay. Is the setup clear? I guess so. No? So one thing that we should start by trying, step one is local anomalies. In this case, we get that I6. So it's going to come from 1 minus 1 over 24, P1 times 1 plus I trace of F, 2 pi minus 1 over factorial, then I. Okay, I want to pick the part of degree 6 here. I forgot the term, didn't I? There's the minus 1/2 trace of a square. There. Okay, so that's the local anomaly. The parts of degree 6 are this bit times the identity. So trace of cubed over 2 pi to the 6 cubed. And these two bits multiplied together, remember that this is degree 4. Okay, well, SG2, the generators of SG2 are traceless, so this part is 0. That's going to happen for any semi-simple group. Here, this in general does not vanish for SUM, but SG2 is a special case where the generators are pseudo-real. in which case you can easily prove that this thing is 0. And that's because the trace in a representation of TA, TB, TC is 0. Okay, so in this case we don't have a local anomaly, and it's tempting to think that you could give a mass term. This thing is almost real, but it's not quite real. So you try to write the mass term for the wire fermion. What do you have? It's a spinor, and it has some index of SU2. You want to make this Lorentz invariant. You want to contract the alpha and beta. This is epsilon alpha beta. And if you want to make it SU2 invariant, you contract the I and the J. But because the fermions anti-commute, they're Grassmannian, this thing is equal to 0. So basically the two epsilons make this thing symmetric, and a symmetric product of a fermion with itself is 0. So I cannot give it a mass term, and there's potential for an anomaly, and indeed, in this case there is an anomaly. So let's try to compute that. According to my philosophy, I have to evaluate the eta invariant on the generators of the Bordism group, omega 5 spin of B SU2. So let's do that next.
Sorry, alpha is the spinor index in that term? Alpha and beta?
Yeah, alpha and beta are spinor, I and J are SU2. Okay, so we want to compute first of all omega 5 spin of B SU2. Then I want to pick a generator of this Bordism group if it's non-zero, and evaluate the eta invariant in there. So in this case, things are understood well enough that I can do it explicitly. So I'll use the Atiyah-Hirzebruch spectral sequence. So I'll explain what this is in a second. It's less scary than it sounds. There's basically two ways that you can sort of approach these computations. Basically, there's two standard techniques, and then you have to apply a bag of tricks. But the standard techniques are the Atiyah-Hirzebruch spectral sequence, or alternatively, you can use something known as the Adams spectral sequence, which is also very useful. So for that, if you want to do these kind of calculations, you probably want to read the paper by Baudry and Campbell. Bell. Okay. This is just in case you think these computations are fun, which are they're actually fun. I hope to convince you of that. And this technique is sometimes very useful, but also it's a bit more abstract, so I'm not going to explain it in the lectures. I'm going to explain the Atiyah-Hirzebruch spectral sequence. And I'm going to specialize it for Bordism. So in fact, this spectral sequence is much more general. It applies to something known as generalized cohomology theories, of which Bordism is an example. But not to have to go into those weeds, I'm just going to present the specific form for Bordism. So if there is, for a vibration, so you have some base, some space X, and some fiber. we have that the following homology groups. So HP of the base with coefficients in the bordism of the fiber. Apats, I will explain what this is in a second. So whenever you have a fibration, you can sort of build the bordism group of the total space if you know the bordism groups of the fiber, which are typically smaller and easier, and you know the homology groups of the base.
Yeah. Did you mean spin theory structure?
Yes. Yeah. A bordism group, bordism structure. Thank you. This was for any bordism theory, and in fact, any generalized commodity theory.
What does the double up mean?
Yeah, I will explain that in a second. Yeah. I think it works best if I explain an example. What it means in some sense is converges. So I'm going to calculate all these groups for any P and Q. That's called the second page of the spectral sequence. And then there's going to be some differentials that can kill some of these groups. They can destroy them. And anything that survives to degree infinity, so there's differential degree 2, degree 3, and so on, anything that survives to degree infinity gives a filtration of this bordism group. A filtration is an ordering of this bordism group. So this is what this means technically. In our case, things are easy enough that these differentials are not are equal to 0, and the filtration is trivial. So I don't have to go into those complications. Okay, so let's compute these things. For my case of interest, so I want to compute the bordism groups for BSU2. So I'm going to choose the following fibration. This is a very common trick. It seems silly, but it's actually very useful. You start with BSU2. And I'm going to take the projection to the base to be the identity map. So I project BSU2 to itself. And the fiber is just the point. So in here, this is X, this is B, and this is F. So in this special case, I have that HP of BSU2 with this thing being the spin bordism of a point about, so sort of converges to the spin bordism of BSU2. So that's what I want, and this is what I need to calculate, and then there's some extra information here that luckily will not enter my calculation today. All right. So the spin bordism of a point, that means a spin bordism decorated with maps to a point. Every map to a point is constant, so I can forget about that. It's the standard bordism. So this is what Max probably called spin bordism groups. And this we know, and it's going to take this result from ABP. Anderson, Brown, and Peterson. So this is it. We have the point, we have the circle with the periodic structure, the torus with the periodic structure, the T3, the K3, bunch of zeros, and then some extra. Okay, so those things you have to take from somewhere. Anderson, Brown, and Peterson, they give you the general formulas. If you want tables, I wrote a paper at some point with Miguel Montero where we computed these tables for many groups at 2 degree 12 or 13 or whatnot. Okay, so that's not too bad. So what I'm going to end up computing then is homology groups of BSD2 with coefficients in Z or Z2. That's already much less scary. SD2 is, one realization is HP infinity, and the Bordism group is unknown. So no Bordism, sorry. The homology groups are known. So HI of BSD2 with coefficients in Z. So this is HP infinity. So probably familiar with what HP infinity means? It's a quaternion projective space. So I'm sure you're all familiar with the real projective space. You get n+1 points, you subtract the origin and you quotient by real scalings different from 0. Complex projective space, the same with complex numbers. Quaternion projective space, the same thing with quaternions. All right, so this is said if I is a non-negative integer times 4 and 0 otherwise. There's different ways of seeing this. You can understand the result from the structure of HP infinity, but it's also quite natural from the point of view of SG2 theories. Remember that this thing classifies SG2 bundles, and this is essentially saying that the only thing that matters is the instanton number in a dimension. So instanton number squared, if you're in 8 dimensions, instanton number cubed, and so on. Okay. So these are the integer coefficient homology groups of BSD2, and from here you can easily construct the homology groups with arbitrary coefficients. So the answer is rather neat. HI of BSD2 with coefficients in omega. Oh, it's a switch notation, sorry. Let me call it HP. That's Q spin of a point is omega Q spin of a point if Q is 4 times a non-negative integer and 0 otherwise. Yes, thank you. All right. So I like to draw these things. So P and Q. P 0, 1, 2, 3, 4, 5, 6. Here let me do 0, 4. I don't need to go up to 5 because I'm going from P and Q to P plus Q. I'm interested in degree 5. So that's as far as I need to go. Okay, so the first I in this sequence is 0. So I just plonk a copy of my Bordism groups of a point here. Z, Z2, Z2, 0, Z, 0, 0. And there's another one at 4. Z, Z2, Z2, 0, Z, 0, 0. Have color, yeah. All right, so the statement of the Atiyah-Hirzebruch spectral sequence is that now that we have computed these homology groups, there's a procedure that gives us the spin Bordism groups at degree P plus Q. So the ones that contribute to degree P plus Q are the ones where So the ones that contribute to degree 5 are the ones where p plus q is equal to 5. So let's look at which ones are degree 5 here. We have this one, and we have this one. So those are the ones that can contribute. And we see that the spin Bordism group is going to be some combination of set 2 and 0, so it's going to be set 2. The thing that kills us for the experts, I'm not going to say much more about this. Before I mentioned that we had some maps, right? We started with this structure, but then there were some differentials that could kill elements. By degree reasons, the only one that can kill us, in this case, potentially, is this map here. It's called D4. In this case, I don't have to do any calculation. Typically, these maps are very hard to describe and to compute. But one property that they do satisfy is that they are homomorphisms. And there's no non-trivial homomorphism from set 2 to set. So this map has to be 0. So in this case, just by staring at this drawing, you can immediately understand that omega 5 spin of BSG2 is set 2. Okay. Yeah.
So in general, we would also need to know the free part of omega 6 in order to get the full anomaly, right? But here, can we ignore it because we just see that this is 0?
Yeah. In this case, yes. That will be the, if you want, in physics terms, the local anomaly. And that's going to be 0. If you want to view it here, the next column comes at 8. And yeah, very good. Any other questions? Okay. So in general, these computations can be tricky, but this one is easy enough that we could do it. Well, there are some subtleties I haven't shown you, but they actually end up not mattering. If you want to see many more examples, so there are some fun things you can do with this. You can check this paper, for example.
So sorry, let's see. So you wanted to compute omega p plus q?
Yeah.
And then there are different choices of p and q.
Yeah.
And then
so you
they give the same answer? Or?
Well, you have to sort of sum over all of them. Or more precisely, they give you some filtration that assembles to the whole omega p and q. In this case, the only things that sum to 5, and they are non-zero, is this one. So I drew everything up to degree 5, so the next column comes at 8. That will not enter that expression. And in these two columns, the only ones that have total degree 5 are this one here, which is 0, and this one here, which is 4 plus 1, 5.
I see, that's what it meant. So this is an E2 page?
That's the E2 page.
I see.
Excellent. And there are some differentials. So for example, the D2 is just going to go 2 places to the left, but that column is 0. D3 is going to go 3 places, the column is 0, and the only one that can matter is D4. But because it's homomorphism, it vanishes.
It's called D4. It's shift the P by 4.
Shifts, I hope I got my conventions right. Yeah, it shifts this by 4 and this by 3.
I see. So in this page, just shift by n and n minus 1, they are all present.
Yeah, it's like a differential in homology. It will increase the total degree by 1, and it goes this way. There's a version of this whole story for cohomology, in which case it goes in the other direction, total degree minus 1. Yep. Any other questions?
I've got a question. So in the original written paper, I think relates it to pi 4 of the gauge group. I mean, this is a more general construction, right?
Yeah.
But can one see from this that like gauge groups with pi 4, or in general symmetries with pi 4 will have?
Yeah, there's a relation between that. So what's the relation? The basic observation is that pi of BSU2 is related to pi of SU2. And to make sure I get the degrees right, I think this is D and this is D plus 1, I think. Can somebody correct me? That's correct, yeah. So this is the kind of thing that we can compute, the gluing of the two hemispheres. This is a bit more natural object when you're computing the Bordism groups, because you can sort of build a space out of simplicial cells, and you're going to encounter this abstraction at some point. Yeah.
But so in the Pointryagin-Thomas construction for the Bordism groups, these are stable homotopy curves, right?
Yeah.
And yet you still get...
I still get the right answer, yeah. So, that's all true, but I don't think I can contribute any insight to that. Yeah, that's true. Yeah. Okay. All right. Anyway, so I explained this for two reasons. One of them is because I think it's good that you see how these things go in practice. They're doable, and when people say Bordism groups of some classifying space, in practice, it's a computation you can do, sometimes.
Can I explain a little more on D4? What I'm trying to say is that there's a diagonal thing, is a P plus 2 to 5.
Yes.
Then there's a map from that row to a row with a P plus 2 to 4.
Yeah.
But that's reduced by 1, not increased by 1.
Yeah.
Degree. So there's a differential map which reduce degree by 1.
Yeah. Sorry, did I say it wrong before? This homology, so it's like the differential operator in homology reduces the degree by 1.
Yeah, I try to say what's homology, because here on this diagonal you get this P plus equal to 5.
Yeah.
Then there's a mapping from this to P plus equal to 4. Looks like.
Yeah.
I see.
Yeah. So
we have this kind of.
Yeah, if it's in homology, it kind of goes in the opposite direction. And it increases the total degree by 1, as it should.
But that's decreased total degree by 1, because that's a map from 5 to 4.
Yeah. So maybe I'm not saying this very properly. There's some differentials that have the properties sorry. There's a homology and a cohomology version of the Th-Hirsebruch spectral sequence. Here I'm talking about the homology version. The degree in the homology, yeah, exactly. The degree in the homology version and the degree in the cohomology version are different for these differentials.
Yeah, I see.
They're of course related, but they're different.
So there's also map from the P plus to 6 down to P plus to 5. But the one that seems so there's a non-trivial one. There's another non-trivial D2 there.
Yeah, let's think about that one. Yeah, exactly. Let's think about that one, right? So there will be another D4 here. That could potentially kill this one. It could do something interesting. In principle, I need to worry about that one. But it's going to come from negative degrees. And I don't have any homology groups of negative degree. But in principle, yes, you need to care about both. Exactly.
Thank you.
Any other questions? Yeah.
So like the anomaly is related with like the presence of one fundamental. Where does appear in our calculation?
I haven't done it yet.
Oh, okay.
So far I'm at the stage of computing omega d plus 1 spin. There's a thing that classifies d plus 1 manifolds, in this case 5-dimensional manifolds with principal bundles.
Yeah.
Now I want to go to associative bundle, pick a representation and compute the eta invariant there.
Oh, I see.
That's the thing I'm going to do next. Yeah.
This kind of thing can also be done when the tangent structure and the internal group are somehow glued quotient.
Yeah, it can be done. This picture is not that pretty for that. Although it's workable. You can do things like a spin C, for example, and you compute the spin C Bordism group of a point, and then if you have another group that doesn't mix, then you can do it exactly this way. But you are going to have to start with the twisted spin Bordism of a group. So the information you need. And for that you have to use some argument, like some sort of homotopy of some space, some Thom spectra or something. So yeah, that's hard work you have to do first. Luckily, it's sort of universal. Once you have that tangential structure, now any symmetry group can be attacked in this way. Very good. Any other questions? All right, so as I said, two reasons. First, to demystify these computations. They are not that bad, really. And they can be difficult, but you know, it's workable. And the other one is because we got that this is set 2, yes, but we got a bit more information. This really comes from H4 of BSU2 with coefficients in omega spin 1 of a point. And this thing is isomorphic to H4 in cohomology of BSU2 with integral coefficients omega spin 1 of a point. Okay, so this follows from the universal coefficient theorem, if you know what it is. And this has useful physical meaning. It tells you that if you want to sort of measure this Bordism class, you probably want to look into something that involves H4 of BSU2 with integral coefficients. That's going to be the instanton number. Or perhaps more precisely, you want to involve C2 somehow. You want to put an instanton in some space. This is naturally a 4-dimensional object. And this is tensor with omega 1 spin of a point. I think Max described. This comes from the circle with periodic spin structure. Okay. So in principle, yes, we have to pick a generator. And in his original paper, Witten picked a slightly different one, motivated by this kind of formula. But if you look at the Atiyah-Hirschberg spectral sequence, a natural thing to consider is some 4-dimensional space with an instanton. Let's take the 4-sphere times a circle. Let's see if we can evaluate the A-time variant in there. So I'm going to take my 5-dimensional manifold to be S4 times S1 with one instanton on S4 and periodic boundary conditions on S1. Okay, there's always a little bit of guesswork involved. You have to pick the right manifold, but sometimes looking at this kind of origin of the Bordism groups can give you very helpful hints. So the result I will quote with a proof. The proof is in the book by Gilkey, for example. Spherical space forms. It's probably in APS also. Anyway, the geometry of Okay, I'll quote the result and then I'll give a physical interpretation. So if some space C is A times B, and dimension of A is odd, and dimension of B is even, then data invariant of the Dirac operator in C is the index on B times the data invariant on C. Gosh, A. There you go. Okay, so what's the idea behind this result? I'll make this a little more precise in a second. But imagine that you have a configuration like this, you have a product, and you do dimensional reduction on B. You're going to get a bunch of massive stuff in A, surviving after dimensional reduction, and zero modes. Massive stuff doesn't give you anomalies, but the zero modes might. So for each zero mode, you'll have an anomaly given by the data invariant capturing the anomaly of these zero modes. In this case, we can do this very explicitly. I will do it in a second. But just looking at this expression, now we can compute the answer. Now it's very easy. In our case, B is the S4 with the instanton, and C is the S1 periodic. Let's put one instanton, just to be explicit. So this implies that this is an exercise I did yesterday. The index of the Dirac operator on S4 is equal to 1. Is the instanton number.
You mean A is the S1 periodic, not C.
Good mention. Thank you.
So you emphasize periodic means you can also choose anti-periodic boundary condition. That will be the wrong choice.
Yeah.
Here the periodic is important.
Yeah, exactly. At this point, you sort of have to guess. I'm not proving that the fact that omega 5 comes from this Etxebarria spectral sequence and this particular term implies this factorization, but it certainly suggests looking at this factorization. Yeah, and because I know that S1 generates omega 1 when it's periodic, that's why I chose that. All right, so the index in here is equal to 1. I computed this yesterday. And the data invariant on S1 periodic. Well, I haven't computed this one. But remember the definition. This is 1/2 of the dimension of the kernel plus the sum. Lambda. It's easy enough to convince yourself that in this case this does not matter. So all this will cancel in pairs. There's always a positive or a negative eigenvalue. The only thing that matters is the dimension of the kernel. And with periodic boundary conditions, the Dirac equation is easy. That's the time derivative of the fermion equal to 0. There's one solution. That's why I chose the periodic. Now it's clearer. I want the periodic because this gives me one zero mode. So this is 1/2. Now, this is the statement, if you want a bit more formally, that the thing that captures omega 1 spin is the data invariant of the fermion. So that's something that I think Max might have said it last week. So with these two together, tell me finally what I wanted, that e to the 2 pi I eta on my space n is -1, and I found my anomaly.
Witten did some kind of mapping torus this year? Or?
In this case, the mapping torus, yeah. In this case, it is, yeah.
Okay.
SymTFT.
Yeah.
Do you know the case if we have the spin which has the Z2 Fermat parity set at the center, and also the SU2 which Z2 center when they are shared?
Yeah.
So this will be spin times SU2 mod Z2, spin times SU2 and model the common Z2. In that case, in your computation, do you recall the way you do this calculation?
Yeah, I will explain that a bit more now. Yeah. Yeah. In fact, here I have a choice that I could have gone differently. For me, I'm declaring that my tangential structure is spin. But as in your paper, it makes sense to also think of this theory as spin times SU2 mod Z2. And that theory can have more anomalies. But I'm not going that way. Just, I chose a specific form for my global form. So if you like, imagine I have a very heavy fermion, which is in the singlet of SU2.
Yeah, can you say more about this sign of lambda, which you cannot? I imagine the partial T per side, this partial T operator have a lot of non-zero eigenvalues.
Yes.
Why those non-zero eigenvalues have no contribution?
Yeah. In general, they don't cancel completely. In general, they don't cancel. They give you some remnant, some fractional number, in the case of global anomalies. In this case, you can prove that every lambda eigenvalue comes with a minus lambda eigenvalue. There's a symmetry in the spectrum. Yeah, exactly.
Symmetry.
Yeah, exactly. So in this case, I wrote the eta invariant, but I could just as well have written the mod 2 index, which is what this is.
Okay, thank you.
And is in this part that you use that we have fundamental of SU2?
Yeah, thank you. Yes, I should have said. When I computed, for example, the index, the number of zero modes goes with the representation. If this was not coupled to instanton, for example, I would have no zero modes in S4. We also proved that yesterday. In the fundamental, you have one.
And if I have like an even number of fundamentals, then?
Exactly. Then you'll get that the index is even, and then the eta invariance is always 1/2, and you get that the exponential of 2 pi I eta is equal to +1. So no anomaly. And in that case, it makes sense because the mass term that I think, yeah, this mass term I cannot write for a single fermion, but if I had two, I can do this, one and the other, and that's a mass term.
Yeah, so maybe that's also related to that. So there's two computers, one is for S4, another for S1. Somehow for S4, you have an SU2 connection.
Yeah.
But on S1, you don't have an SU2 connection. So that became a spinless fermion. There's a
kind of, yeah, exactly.
Yeah.
Let me say something about that because it's subtle and interesting. So I was mumbling something about dimensional reduction. We can make it more precise, right? So if you reduce a fundamental fermion on S4 with one instanton, you get a zero-dimensional theory of a Grassmann variable, so something like a matrix model. And what does this couple to? Well, it's a fermion. It will couple to the spin bundle. But there's also a fundamental coupling to whatever remains of the gauge group that communes with the instanton. That's going to be the center. So there's an effective gauge theory. This fermion is charged, but I'm not going to put a bundle of this type. But the following things happen, which is interesting. I'm choosing the periodic boundary condition. One thing that's fairly unintuitive, but true, is that if you're thinking of the periodic boundary condition of a fermion, and you think of this in terms of a mapping torus, under a torus, what is just a line. when you glue the fermion, you glue it with -1 to the f. Right? This might not be familiar to everybody, so let me explain it, or at least mention some similar phenomena. So when you're computing the thermal partition function of a fermion, if you want to compute trace of e to the minus beta h, that's the antiperiodic fermion boundary condition. Into the supersymmetric boundary condition, you introduce -1 to the f, which happens to be the periodic one. So that's an example. If anyone wants me to explain this better, I can do it. I can do it later. But hopefully, it's a familiar fact to most of you. Now, in this case, and that's something I think Juven was alluding to before, perhaps, -1 to the fermion acts on the fermions exactly like the set 2 in the center. This is the fact that in this theory I could have chosen the gauge group of the tangential structure to be a spin times SU2 mod Z2. The center of SU2 and the spin act on exactly -1 to the f act exactly in the same way. So you can view this map in torus as one that has a holonomy that you glue with this center of Z2. And the fact that I picked up a phase now means that the effective theory in 0 dimensions picks up a phase when I translate with a gauge transformation, with a glue with gauge transformation. So this theory is anomalous in the standard sense. The measure is not invariant under gauge transformations. Okay. Yeah, but yeah.
At some point you mentioned the near anomaly by Wang, Wen, and Witten.
Yeah.
Where does this come from in this setup?
If I remember properly, and 2 of the authors are in this room, so I'm more than happy to be corrected. But I think they choose a tangential structure which is different, which is a spin force times SE2 mod Z2. Now, because you have a different tangential structure, some of these details are different. So, for example, the spin bordisms of groups are different and so on. And you find different item variants, more manifolds if you want. So perhaps the key point here is that there are more manifolds that have this tangential structure than manifolds that are spin. In the same way that there are more spin-C manifolds than spin manifolds. Yeah, is that fair? As a zero order approximation to your paper. Okay. So one of the exercises I put, which you haven't seen yet, but hopefully I can circulate them later today. You can use this kind of argument very productively, this dimensional reduction argument, to sometimes compute complicated anomalies in higher dimensions that will involve very high degree bordism groups. So typically these calculations get much harder the higher you go in degree. You can dimensionally compactify in clever ways and reduce to simpler problems. So that's a technique that in some cases has yielded very useful results. Okay. Any questions? I realize I have said approximately 0 about string theory so far, so that's going to change now.
I have actually a somewhat naive question about the global anomaly.
Yeah.
Like, if I'm just interested in like particle physics and like computing correlation functions in flat space-time,
yeah.
This anomaly appears somehow, or like is like the theory you defining even in this scenario, or
here there's a useful distinction between anomalies which are local in space-time and anomalies which are global in space-time. So by that I mean anomalies that you can detect in a mapping torus, and anomalies that you cannot, basically. And even stronger than that, picking this manifold to be S4, so neighborhood of a point. So you have an anomaly like that you detect by looking the neighborhood of a point. Even if it's a global anomaly like this one, it's going to be very difficult to fix. The reason is that you can have one of these item variants, but sometimes you can cancel this phase by coupling to some topological field theory that has the same anomaly, and that will not change your local degrees of freedom. So an experimenter will see the same thing, and there's no useful constraint coming out of that. But you have an anomaly that you can detect, even if it's global in S4, then in the neighborhood of a point, the topological field theory is going to contribute in there. So those ones are much more dramatic in a way. If an experimenter came and told us that, they found an SG group and a single fermion which was massless and nothing else, we'll tell them, well, check again, because we did something wrong. But some of these more complicated anomalies, sometimes they can be cancelled. Some of the time-free anomalies. So I think an example I like, there's a time-free anomaly if, so there's a symmetry of the standard model that we typically don't talk about too much, which is roughly the square root of -1 fermion. So what do I mean by this? It's a symmetry that let's see, for all the gauge bosons in the standard model gives 0. It's a set, sorry, this is set 4. For the fermions you give 1, and for the Higgs you give 2. And you can check the Lagrangian of the standard model, and you see that this is actually a symmetry of the standard model. The fact that this is set 4 implies that you can choose a tangential structure for a standard model, which is spin times this set 4 mod set 2. And if you choose this tangential structure and compute the die-free anomaly, it tells you that the total number of fermions in the standard model has to be a multiple of 16 in any consistent theory. That's wonderful news, because if you go generation by generation, you find that in one generation you get 15 fermions if you don't include the right-handed neutrino, and 16 if you do. Wonderful. So that's a beautiful result, but in some cases you can also cancel this anomaly by a gap sector, as Juven showed at some point. So these anomalies are not as powerful. Certainly suggestive. The fact that this is 16 is suggestive, but it's not a proof or anything. Okay. I don't see any other questions, so what I'm going to do is, I think I'm supposed to stop here, correct?
More or less the time.
More or less the time. So what I'm going to do in the next lecture is, so far I have talked about fermions, chiral fermions. Of course, there's other things in the world. For string theory, we care about gravitinos and self-dual forms. I will explain anomalies for those next time, and show that the string theory is anomaly-free.